Thanks everyone for coming. Can you all hear me okay? Yeah, good. Great, yeah. So Strange Loop is like far and away my favorite conference, like amazing talks and really great attendees, and yeah, I'm really honored to be here, and I really appreciate you came and came to hear about our work. So yeah, today I'm going to be sharing some of the work that we've done at Outer Labs related to generative building design. So over the past few years, we've been building out a platform that designs commercial office buildings, starting from understanding things like site constraints and then moving into form generation, and then actually goes all the way through like laying out desks and other spaces, creating full test fits. But before we dive in, I can tell you a little bit about myself. I'm Jen Carlile. I've been working at the intersection of technology and the built environment for a little over a decade now. This is me when I was about 2 or 3, just a little bit older than my own little daughter, who's actually here at Strange Loop with me, so never too early to cultivate a love of technology. But I started my career as a software engineer back in the kind of early mid-2000s. I started by writing mostly C++ related to digital audio with a little bit of like low-level Windows drivers work sprinkled in. But I pivoted into AEC, or architecture, engineering, and construction technology around 2010. And now I'm a co-founder and CTO at Outer Labs. And we're focused on custom software development for large real estate owners, in particular tech companies that have kind of complicated real estate portfolios. So here are some team pictures from an offsite we had earlier this year in Austin. We're a remote-first company, so getting the team together, something we try and do at least a couple times a year. We're now about 50 people. We've got a few people from Outer Labs here too. We're distributed all over the US and even have a few people in other parts of the world. So our work focuses on commercial building design, office space in particular, and I'm guessing not a lot of people are in the audience are familiar with building design processes, so I'll give a brief overview just to help orient folks. So the traditional design process is still quite manual, with dozens, sometimes like hundreds of people involved. It starts with the owner who wants to commission a building. They typically go on to hire a team of specialists from different firms with different specializations. So just to name a few, architects would determine like site constraints, explore building form, mechanical and structural engineers, design the building systems, facade consultants like design the exterior of a building, interior architects create spatial test fits, building code experts like make sure everything's up to code, and like the list goes on and on and on. As you might imagine, with all of these moving pieces, all these different people, there's a ton of complexity in communication. People often work in silos, and a lot of rework happens if something upstream changes. So say like if a building facade changed from masonry to glass, it might be necessary to like completely redesign like the entire HVAC system due to like different thermal loads on the building facade. This also means that iteration is not particularly fast in building design. In fact, it's often like quite painful. So something that you'll commonly see is that 2 or 3 design options are identified upfront and then developed in parallel. And like, yes, having 2 or 3 design options is good, but you have to wonder like what sorts of possibilities are unlocked if you could explore like 100 or 1,000 options in the time it currently takes to explore one. And that idea is really at the crux of the work that we've been doing. Like, what if there's a better way to design buildings where like the fundamental rules about how a building should manifest are like encapsulated in a repeatable process that can be run in seconds, while still preserving the ability to express like complicated and compelling forms. Like nobody wants to live in a world full of like boring rectangular boxes. So whatever work we do, needs to support like variety and form, and a lot of different aesthetics. So I'm going to take a short detour for a moment and just talk about something that's provided a lot of inspiration for me over the past 10 years, which is trees. Monterey cypress trees in particular. So has anyone here ever been to like the central coast of California, like Monterey or Big Sur, Carmel? Yeah, a lot of people. It's a really beautiful place. And Monterey cypress trees are really common along the Central Coast. You really can't go far without seeing one. And I think it's one of the most beautiful trees on the planet. And what makes it beautiful to me is that the Monterey cypress, like more than most any other tree, really expresses uniqueness by adapting to place. So you get these very beautiful, like windswept forms, very organic, that are heavily influenced by the wind patterns along the California coast. So what's neat is that with all these different forms, I'll just show a couple pictures. You know, they all look quite different. What's interesting though is they all come from the same seed. And in the seed are kind of all the rules that this tree needs to like grow and develop. And if you take 5 seeds from the same seed pod and you plant them in like 5 different locations along the coast, you're going to get 5 really different trees because they're subject to different wind patterns. But if you take the same 5 seeds, and I think this is equally as interesting, if you plant them close together, you're probably going to get 5 very similar trees because they're kind of subject to the same wind patterns and growing under the same conditions. So, the way that we design buildings today is kind of like if Mother Nature designed every single tree from scratch, which, clearly does not work for her, so why should we be satisfied with it? And with our work, we ask, what if we stop designing individual buildings and start, thinking about designing building seeds, seeds that can like take on different forms, different characteristics, depending on where they're planted. And if we start thinking in this way, we can really increase our leverage and get to the point where, we can explore like 100 or 1,000 forms in the time that it currently takes to explore one. So, yeah, the title of this talk is Designing Fully Rationalized Commercial Buildings with Generative Software. So far we've defined commercial buildings. So in our case, this is office space, but we haven't yet defined the term fully rationalized. So what do I mean by that? In building design, there are different phases of design, and in each phase, more detail gets added to the design. So the phases are generally referred to as pre-concept, concept, SD or schematic, DD, design development, and construction documents. And nearly all the big decisions in a building design are made before CD and by the end of SD. So, like what's the form going to be? What's the site placement? What sort of HVAC system is it going to have? So we focus our work there in order to kind of have the most impact. So when I say fully rationalized, that's what I'm referring to, is something's designed to a schematic level of detail. So one of the first things that we did in our work was to lay out the flow of designing a building in a linear sequence. So almost always the process starts when like a business need is identified for more space, but we won't go into that here at all. And we'll solely focus on the design process. So, the first thing that happens is a site is identified. Depending on where the site is, there will be different rules and regulations on, how the site can be used, how large of a building can be built there. And, zoning varies from city to city, and it can even vary from like block to block within a city. And usually a specialist is hired here to determine like what's the buildable envelope for a site. And this provides like the volumetric boundaries for the building to be built. Often it's like a simple lofted polygon, but other times it can be like a super complex form with different planes of varying heights, cutouts that like slice away from the envelope. I think this is a really interesting one. This is like a super complex buildable envelope. This is actually from a project that I worked on back in the early 2010s. You can see there's like a cylindrical cutout because there's what's called a heritage tree. There's like planes of different heights, and then you have this like blue plane that's actually called a view corridor because this building in particular was near the Austin Capitol building, and so you couldn't block the view there. But more often than not, they actually look more like this, a lofted polygon with kind of varying setbacks from the lot edges. So the next step after you kind of understand site constraints is typically determining what's called the program for a building. So this basically says how much and like what sort of space should be included. Like in our case, how much desk area, how many conference rooms, what sort of conference rooms, what sort of amenities. Like is this building going to have a cafe or bicycle storage, et cetera. And then once you have your site constraints plus your building program, you can start exploring building form. And this is where architectural creativity really shines and comes into play. So I'll do a deeper dive on this in a few minutes, but it's a really cool area. So at the same time that we're exploring form, we're also doing what's called a macro layout. And this defines roughly what parts of the building are going to be used for what. So here it's color-coded. Light blue is office space, dark blue is meeting space, yellow is amenity spaces. So once a form and macro layout are identified, the next step is to establish the structural grid and structural member sizing for a building. So you want to determine how large are the beams and columns. And the next, totally separate from their physical locations in space, elements of the MEP system, so mechanical, electrical, and plumbing, these systems are sized. And what we're trying to figure out here are things like how large does an air handling unit need to be, or a boiler or chiller for a building. And then once we know how large the elements of an MEP system need to be, we can start to place them in physical space in what's called the building core, along with the vertical transport and stairs, so elevators, stairs, things like that. And then the next step is to take the secondary kind of smaller core items and place those in the building, which is typically adjacent to the larger primary building core. And then with these major pieces in place, we can start to think about the layout of the space. So we first start with primary circulation, so that's the red lines here, and then we also think about secondary and tertiary circulation. And then once that's designed, we actually lay out the space with the contents of the program. So we start, because we're working on office spaces here, we start with the workspace itself, like the desks and where people actually get their work done. And then we can layer on top of that conference space, amenity space, and other things like that. And then finally, there's typically a step related to seismic design, where the structural system has additional pieces added to it. So it's typically either moment frames or shear walls, depending on the structure type. And this is to protect the building in case of an earthquake. And while this is a pretty simple diagram, each step in this flow represents the work of many people, dozens of people, each with very deep subject matter expertise. And we don't have all of that expertise in-house at Outer Labs, so our approach was to actually partner with forward-thinking AEC practitioners and basically sit with them to understand what are their basic algorithms for doing their work, and then translate that into software. So related to site placement, we worked with architects to see how they think about zoning, building placement, access, and things like that. So besides the buildable envelope, which volumetrically constrains what can be built on a site, there are also considerations around things like where should parking go? We live in a car-centric society. Where should the main entrance be? Where should things like a loading dock go? And then once the site is understood and we have a program, the next thing to think about is to think about form. And there's a term in architecture, a partie, which is defined as the organizing thought behind an architectural design. And this slide has a few pictures of different parties. We have the weave up here in the corner, steps and ramp. And some of the names are really kind of descriptive and obvious. Others are a little bit more abstract, like the canyon here. So in kind of the north and south parts of this building, the cutout is meant to feel like a canyon, and the building walls are meant to feel like canyon walls. This is another fun one too that we worked with called the playa. The organizing idea here draws from kind of the Burning Man ethos, where individuality and self-expression are very important. And with this partie, the idea is that inside, the space is highly configurable and can be made to fit the needs of a team or individuals, in a self-service way. And when we talk about parties, there's literally an infinite number of parties. It's just based on human creativity. But there are ones that you'll see kind of over and over again in building design, like letter-shaped buildings, like T's and L's, and O's and U's, courtyards, things like that. So form generation, like I said, was a really rich and interesting area of our work, and it's a place where creativity can play a huge role. And while most office buildings don't look like these crazy things, many building owners do express their brand and identity with their office space, and hence really wanted to make space in the tools for creativity and uniqueness. So I'll go into this in a little bit more in a couple of minutes. On the building system side of things, for this project, we primarily focused on the structural system as well as the HVAC systems, and translating these algorithms for structural, working with structural and mechanical engineers was a bit more straightforward than trying to think about how do you encode building parties into software. So the general process that we followed here was that building engineers would basically express their logic as flow diagrams, and then we'd translate that into software. And they'd also provide things like formulas and lookup tables, often straight from engineering textbooks or building code guidelines. For structure, we focused on two different structure types, steel and mass timber. And I think most people are familiar with steel as a building material, but maybe fewer with mass timber. Mass timber is kind of shown in here. The way it's constructed is it's multiple solid wood panels that are either glued or nailed together, and it's very strong, it's very stable, and it's also very low carbon. It's a great alternative to either concrete or steel if you're really going for a low carbon building. It's also really beautiful and creates this sense of visual warmth. It's makes a nice space when you're in it, as you can see from this rendering here. And for either structural type, the basic process was the same that we followed. So once we had a macro space plan for the building, we'd establish the column grid for the building, assume certain loads based on how the space was going to be used, and then calculate the size of the beams and columns that were needed. Also, we calculate a set of metrics related to the structure, namely framing weight, which can be used as kind of a proxy for cost. In general, the lighter the structure, the less it's going to cost. And then another interesting metric we had was called structural irregularity. And in general, the lower the irregularity score, the simpler and hence less expensive it is to build. And then the last metric that we talked a lot about was embodied carbon, because as we were building out this tools, we wanted the platform to really create the best buildings possible that had the lightest footprint. So here is, let me start this video. So this is a video looking at different design options related to structure. So you can filter by the structure type. First we look at steel and then mass timber, and I can see metrics about it. And then here I choose this is a mass timber option. I compare it to steel, and you can see, side by side, how are these two options stacking up. And the place you'll see the biggest difference is obviously in the embodied carbon metric, and it's much lower for mass timber. For the building's MEP systems, we were less interested in optioneering, in the same way that we were for form, and even to some extent the structural system comparison. So the client that we worked with to build out these tools had really strong guidelines around what does good look like with respect to HVAC, electrical, and plumbing. So in this case, it was more about modeling just a single path for designing each of these systems, and then reporting out metrics about them. And then lastly, we worked closely with design leaders from our client's firm and other interior architects to actually lay out the floor plates of the buildings designed on the platform. This particular client had a really strong sense of how space should be laid out and how it should function. So we worked with them to create basically parametric expressions of the building blocks that they would then use to lay out the space. And using a library of assets to lay out space is not a new idea at all. But what is a new idea is kind of making those assets able to grow and shrink to fit the space that they're going to occupy, and then also giving those assets enough intelligence to know how to arrange themselves within a building on a floor plate. So when you bring it all together, what we have is a generative building design tool that creates, rationalized building designs in just a few seconds. So, and the point of this is not just to have a faster design process, but it's really ultimately to arrive at a better starting point for building design. So let's see the whole thing in action. This video demo is about 3 minutes long. Okay, so we will get it. Yeah, so here we start with the site. And the first thing that you see is the buildable envelope for the site here in purple. And then we can modify some of the setbacks and kind of change the envelope to see how to be how we'd like it. Now we can look at some of the targets for the building. It's around parking. And then in the same tool, we can go and look at the program for the building. So we're defining what kind of spaces, how many, in what ratios and quantities should they be in the building. And then we can also take a quick look at the budget, target budget. It's broken down by hard costs and soft costs, and you can drill in much more deeply. So next we move into form generation. So we select a few different parties and then can explore the forms that are generated. So here there's probably a dozen or so different parties that are available. We select a few and look at what the results are. Anything that we like, we can favorite and save for later. Filter out a few different parties. And then if you want to just do a really quick side-by-side, you can select, a few of the different options and then see, up here in the left, the spider diagram, you can see the different options overlaid. Or if you want to look in more detail and do a more like side-by-side, deep dive, apples-to-apples comparison, you can go into your favorites and then see these buildings side-by-side. Sorry, I think my video is experiencing a playback issue. Okay, seems like it's starting again. Maybe? Sorry, getting like the white spinning wheel. Okay. Yeah, so I hope the video stays playing. Anyway, so what the tool is showing here is actually going in and modifying the form that is generated. So the idea here is really like the tool generates a starting point for you, and you can go in and change it and kind of go from there. So the first thing we showed was just changing the space categorization by basically taking some of the workspace, converting it to meeting space. Here you can actually modify the form by adding and removing voxels here. This is more just to show how it works. And then once you are happy with the form that you want to pursue, you can actually go and do a more detailed spatial layout. So we go with one of the other options that was considered this sort of like 3 offset bars. The first thing you do is plan out the circulation. You can go in and make modifications to it, copy it from level to level. And then once you have this set, you can actually move in and start creating a full spatial test fit here based on a target program. So there's a constraint solver running under the hood of the program that takes in a target program and then produces many different outputs. You can go in to any local neighborhood and kind of examine its contents and give it a different target and ask the constraint solver to replan it. And then, as in life, there's always more than one good solution. So what you're seeing at the very end here was the tool presenting a few different options that a person could then choose from. Okay, so now that you've seen the whole end-to-end process, I wanted to do a deeper dive into form generation because our team found this to be just a really interesting and challenging area of the work. So like I mentioned earlier, when someone thinks about architectural creativity, you often think of form. It's, the practice of architecture encompasses a very wide range of things, but physical form is really like one of the most visible aspects of architecture. So I'll start this video. So one of our early experiments in form generation took the form of an optimization problem. So we set targets for things like square footage, window to wall ratio, daylight access, and more, and then kicked off a routine to explore different forms. And in this video, you'll see that there's the smallest atomic unit that we're working with, a block or a voxel. This represents like the smallest spatial change. And we elected to go with what's called a building structural bay, which is basically the space between columns for this. And while this was like conceptually a very interesting approach to form generation, we ultimately ended up with a lot of kind of blobby buildings. And they just didn't really pass the architectural sniff test. You can argue that some of these forms are like highly optimal for the targets that we were setting out, but you'd ask an architect and they'd say like, that doesn't look like a building, or like, what's the rationality behind that shape? And so this caused us to go in a different direction. I'll start this video. So the next route that we explored was that of creating forms based on architectural parties that I've mentioned now a few times. So again, that's kind of the organizing principle behind a building form. And this is a short video of our partie machine. It's a visualizer that starts with a basic shape like a U or an L or a T, then applies a program breakdown to it. So the different colors represent different space types. It's a little confusing that these colors are different than the ones I was showing earlier, but it's the same idea. And so as the building grows and shrinks, the ratio of the space types remains the same. And then finally, I guess this is just showing a few more explorations of form. Kind of mesmerizing. And then finally, we would apply like a vertical extrusion element to it. And so what you're seeing is this model kind of exploring parametrically, trying to hit space targets and program targets. And, this is, with these explorations, we started to get a lot closer to like architect-approved buildings, and ultimately ended up going this way in the tools that we built. So then the next step was to decide like which building parties to include in the tool. And we worked with a fantastic firm in New York called BIG. It's short for Bjarke Engels Group. And with them, we defined a set of parties that could be encoded into the tools, along with like the parametric rules and how they would grow and shrink. This is a picture of the team from the BIG office, that's me. And these are some 3D models of some of the parties that we explored. And this is how it ultimately manifested in the tool. This is an animated GIF. So we had a handful of basic partie shapes like rectangles and courtyards, U's, L's, and T's, plus the more custom parties that we worked with BIG to develop. And so when a person creates a new project, the form generator module like creates many, many different form options based on these parties, and then a user can filter through them, page through them, page by page, and explore the different forms. So another area that I wanted to do a deeper dive on is metrics. So metrics are actually like the so what of all of this work. At the end of the day, the goal of the work is not just to design buildings faster, but rather to end up with like better buildings that perform well for end users. And without metrics, like for every building that the platform designs, the comparisons are just really subjective and kind of arbitrary. So, I think as engineers and technologists, we all understand and appreciate data-driven approaches to our work, and we think it's absolutely the same for building design. So in this tool, when we design a building, we like measure the heck out of it. We of course start with the basics like square footage, how many people can this support, what's the cost per head count, and then evaluate like more performance-focused metrics. And these are things like flexibility, like how easy is it to reconfigure or repurpose the space, daylight access, distribution efficiency of the MEP system. And then, for each building system, there's a set of metrics too. So once we have all these metrics, we wanted to make it very easy to compare building designs, kind of apples to apples. So you visualize all of the metrics up in the spider diagram here, and then you can very easily just kind of see how the buildings stack up. Also, if you want to kind of drill into more detail, you can look at things side by side and see how things compare, like apples to apples. We also spent a lot of time looking at like what I was calling like our squishy metrics, metrics that are like maybe a bit harder to like quantify or express as like a single numerical value. And this turned out to be like super interesting. And one of the things that we care a lot about for buildings that the software generates is like, are they going to function well for their end users? Because we've all been in a space that feels good to be in. You want to be there, you want to spend time. We've also been in spaces that feel bad and you just want to get out of there as soon as possible. And there isn't like a standard way of measuring space. So we started working on it, and we thought it was really a valuable endeavor to at least try. So one of the first that we looked at, and granted this one is a bit more standard of a metric, is daylight access on a building floor plate. So daylight access here is visualized as a heat map on a floor plate. And the way that we calculated it is from a collection of points on the floor plate, basically every desk and then other locations as well. We would raycast radially from that point, and then do basically a weighted average of the distance to the closest facade and take into account like the cardinality of that facade, because if we're in the northern hemisphere, southern facades get a lot more daylight than say like a northern or a eastern or a western facade. And then we take that and produce a basic heat map. Another interesting metric that we focus on, and one of the more squishy ones, is called buzz, or like how lively does a space feel. And this metric is really an important one for like how occupants feel in a space. Like, does it feel alive and occupied, or does it feel empty and quiet? And so the calculations for this, have a lot of assumptions built in around like how is the space used, how frequently are people coming into the office, what are their usage patterns. But even in this first iteration, we had a lot of really interesting, valuable insights, and it sparked really interesting conversation. And we could obviously take this a lot farther, and I hope we have a chance to in kind of further iterations of the tools. And metrics are so important that we don't actually frame this as a generative design platform, but rather as a data-driven design tool that provides information that can be used to like quantify a building design and ultimately produce a better building for occupants. And as we rolled this out to users, it was really cool to see the collaboration that it unlocked. So last year we held a multi-day on-site charrette where project teams made up of like cross-functional disciplines like architects and building engineers and interior planners. We all came together and then used the tools in real time to develop building designs. And like one exciting thing we observed was, I remember it very vividly, there was an architect and a space planner sitting together and like making adjustments in real time about the space. So they'd say, like, oh, what if we bumped out this wall and added an amenity here? What if we pulled this wall in? And so they were like in real time running what if scenarios that like, if this were the more traditional design process, those iterations would have taken like days or weeks, or if they would have even happened at all. So that was really cool to see. And then, one big takeaway from the work is that while it's like conceptually very interesting to have like a fully automated generative design process, the value comes not necessarily from like the end result, like the designed building, but rather in providing practitioners, these subject matter experts like architects and building engineers, tools so they could like quickly explore the questions that they wanted to answer. In the scenario that I just talked about, like it was really cool to see the architect and space planner kind of going back and forth, collaborating on like how a particular region of a floor plate should be functioning. And as we work on the next iteration of the tools, this is something that's really like front and center in our work. How can we provide tools that help with the particular task at hand, whether it's like defining a building program, generating a spatial layout, estimating a budget, and then like seamlessly tie all these things together so that if something changes upstream, anything that's downstream can easily be affected by that. Yeah, so just to wrap up, I just wanted to thank everyone for coming today and listening to me talk about this work. We're certainly not the first people to think about how computers can help design buildings, but I feel like we've taken the idea in like a really compelling direction and like shown what can be unlocked when a traditionally like sequential and siloed process is really thought of holistically. And this isn't a commercial product, so we don't have a chance to really talk about the work very often. So I'm really happy to come here and kind of share about it. And thanks for coming. And I think I have a couple of, I think we might be right up on time. If anybody has any questions, you can find me afterwards. I'm on the Strange Loop Slack channel and easily reachable. So thanks, everyone.